So my name is Jane Wong, and I'm the director of Invited Talks for UQC this year. It's my honor to welcome Professor Stephen Girvin to begin our undergraduate accessible speaker series, which will run throughout the spring semester. Professor Stephen Girvin is a Eugene Higgins Professor of Physics at Yale and the director of the Co-Design Center for Quantum Advantage at Brookhaven National Laboratory. He also serves as a faculty advisor of UQC. You will also have opportunities to ask Professor Girvin questions after his talk, moderated by our president, Transistor. Without further ado, I will let Professor Girvin get started.
Okay, thank you very much for the invitation. It's a pleasure to be here. If you want to use the raised hand feature under participants, I'll try to keep an eye on that. And it's fine if you interrupt with questions. I have lots of stuff here and I don't have to finish it all. I'd rather you understood things than I just covered too much. So we have probably a fairly mixed audience. Some of you are semi-experts on quantum information. Some of you are complete beginners. So I have pitched the beginning portions of the talk at a fairly low level. So apologies to the experts, but we're all trying to learn together, and it's better for me to keep it simple at the beginning. So as mentioned, I'm, in addition to being a physics professor at Yale, I've recently temporarily taken a half-time appointment at Brookhaven National Laboratory, which is just across Long Island Sound. From here, you can get there on the ferry from Bridgeport. And I'm running one of the 5 national quantum information science research centers that were recently funded by the Department of Energy as part of the US National Quantum Initiative. And there are 5 federal labs, 18 universities, plus IBM as our industrial partner, 88 principal investigators, and soon many graduate students and postdocs. And we're trying to move us out of the current so-called NISQ era, noisy intermediate scale quantum systems, into the era of useful quantum computers. So now if I can get the slides to advance, that would be very helpful. And there we go. So we're actually in a second quantum revolution. The first quantum revolution began more than 100 years ago and brought us the technology of the transistor, the laser, and the atomic clock. And those in turn brought us the technological revolution of the 20th century. But the inventors of quantum mechanics were thinking about sort of the nature of reality and just doing curiosity-driven research. They did not foresee the invention of these quantum devices. And even the more practical people who invented these quantum devices did not foresee their applications. And the thing that we now understand is that these are quantum devices, but not very. They do not use the full power available to quantum machines. What do I mean that they're quantum but don't use the full power? Well, you need the quantum theory in order to predict the parameter values of these devices. What is the frequency of the laser? Well, you have to know the quantized energy levels of the atoms. What is the threshold voltage that turns on the transistor switch? Well, you have to know about the electronic bands in silicon. So you need the quantum theory to predict these properties, but the voltages and currents and electric fields that are there when these things are operating are largely classical. There's really no difference between a laser, the sort of sine wave of electric field that's emitted by a laser, and that's emitted by your favorite radio station. And the voltages and currents in transistor circuits are, you don't need quantum mechanics to describe their operation. So here's the first transistor that was hand assembled at Bell Labs in 1947. It's it's a quarter-inch across or so. You can see those solder blobs, and it's a point contact between two different semiconductors. It's a complete mess. But it worked, and it was invented for a specific purpose to amplify signals and replace the vacuum tube. But these people who won the Nobel Prize, this was John Bardine's first of two Nobel Prizes for inventing the transistor, uh, could not foresee the uses that we have today, that they could be made much smaller than this, put into integrated circuits. And they certainly could not foresee the current rate of transistor production in the world today. That number, I don't know if you know what it is, but it's enormous. It's more than 20 trillion transistors per second, every minute of every hour of every day of every week. It's just a stunning number. And obviously, if you're going to make 20 trillion per second of anything, those things had better be pretty small or you'll run out of stuff. And it's just an amazing technological advance from here to 70 years later, to this area. And so all of this is to say that give me protection if I try to talk about the future of quantum computing. Making predictions about the future is difficult. But there's now a second quantum revolution underway in the 21st century based on not a new theory of quantum mechanics, it's the same theory, but a new understanding that quantum machines can be built that have more power than we had imagined before. And there are it's a three-legged stool. It involves the study of what are called quantum materials, materials that have strange correlations among their interacting electrons and interesting transport properties. I won't be talking about that. Quantum sensing, we now understand much more about the uncertainty principle and how, in certain cases, to defeat it, to be able to detect the tiniest signals, for example, the tiny vibrations of space-time when gravitational waves are released by merger of black holes. There was an experiment at Yale in the Wright Laboratory called Haystack, searching for dark matter candidates called axions, which can be detected using the technology that was developed for superconducting quantum computing. And there are many other things you can do. You can sense, you can do nuclear magnetic resonance structure determinations of single molecules. And finally, there's quantum computing, simulation, and communication. So quantum information processing. The field of computer science was really put on a firm theoretical basis 100 years ago, 90 years ago, by Church and Turing, who thought about what is a universal computer, and who's laid the foundations for theoretical computer science on what is computable, how can things be computed efficiently, and so forth. And they did not take into account the possibility that the hardware might be quantum. And this is now realized is really overturning the foundations of that part of theoretical computer science because of the different capabilities of quantum hardware. Now, quantum states do hold information in ways that we now understand much better than before, but they're extremely sensitive to small perturbations and the fact that when an observer observes something about a state, it changes. That's extremely good if you're trying to build a sensor. It's extremely bad if you're trying to build a quantum computer. So this is the engineering challenge that we're facing in the computing world. So we're currently in this so-called noisy intermediate scale quantum era. We've invented the quantum abacus, or maybe the quantum vacuum tube, maybe the quantum transistor, and we're trying to build the first quantum integrated circuits. So there exist rudimentary quantum computers, very rudimentary, but they don't work very well yet. So you should think of us as being in the era of the 1940s, maybe, with multi-ton vacuum tube computers that didn't work very well. So, so now we're in this new era in the 21st century of this second quantum revolution. And quantum computing is a completely new way to store and process information. It uses this concept of superposition that you, if you've had a course in wave mechanics, quantum mechanics, you know waves can be superposed on top of each other. And in the case of quantum bits, there's an inaccurate but simple statement that is often made that the advantage comes from the bit being both 0 and 1 at the same time. It's kind of a reinterpretation of the uncertainty principle. You don't know whether the bit is 0 or 1. That sounds bad, but there is some sense in which it's potentially could be both. That's actually strictly not correct. Bits don't have values before you measure them, but this is a convenient shorthand. There's entanglement, which is multi-qubit superposition. And entanglement leads to non-classical correlations between the states of distant qubits that are stronger than is permitted classically by things that have values before you measure them. And it allows very strange things like teleportation of states or gate operations to distant parts of the computer. And this was the thing which Einstein understood better than some of the other founders of quantum mechanics. And it was the reason that he felt quantum theory had to be wrong. He just felt the spooky action at a distance associated with entanglement meant that the theory was incomplete. So a real irony is that we use every day in Becton Lab this spooky action at a distance as an engineering and calibration test. We do things that Einstein said were impossible just to make sure that we really do have a working quantum computer and not a classical computer. So I think if Einstein were alive today, he'd actually, he might argue with us for a while, but I think he would eventually be pretty impressed. So let's see what happened to my, yeah. So this combination of superposition and entanglement leads to a kind of massive parallelism where many computations can be done simultaneously. You can, in some sense, give the computer at its input register a giant exponentially large superposition of every bit of input data you could ever give the computer. And the Schrodinger equation is linear, and so the solution as the computer marches forward in time works on all of those elements of the superposition simultaneously. That's the good news, so tremendous speed up. The bad news is that when you measure at the output, you get a random state collapse to one of the possible solutions, not necessarily the correct one. But this ability to perform certain computations that are essentially impossible on any conventional computer is not because the clock speed is faster, but rather the complexity of tasks scales differently with problem size. Like the runtime might be the number of numbers in the database to some power, or it might be exponential. And for a classical algorithm, it might be exponential. And for a quantum algorithm, it might be polynomial. And so if you get large enough problem size, even a slow clock speed will not prevent the quantum computer from being faster. But that's only the case if you can handle large problem sizes. And so far, we can't. We're still trying to build large-scale computers. So what powers do quantum machines have? Let's say quantum computers. Well, computer scientists like to classify problems in with a complicated scheme about how easy they are to perform on classical hardware. So multiplication is easy. I can do it on my iWatch, my iPhone watch. The reverse factorization is extremely hard classically, as far as we know. If I give you a giant number and ask you to find the prime factors, that's very hard. Although once you have them, it's trivial to check that they're correct. It turns out on quantum hardware, Peter Shor invented this Shor factoring algorithm that makes factorization exponentially faster than any known classical algorithm. Also, if I give you a quantum state, what's the wave function for the electrons in an atom or something, then, and I give you the Hamiltonian, the energy, you can evolve that forward in time on a quantum computer very, very efficiently. Many people loosely say, oh, you can solve all kinds of quantum problems with a quantum computer because it uses quantum. But in fact, the problem of finding the ground state of a collection of electrons in a giant molecule is actually, in general, quantum hard, even for a quantum computer. But still, we believe there are going to be people are working on approximate algorithms and so forth in quantum chemistry to work these problems faster someday, we hope, than on classical computers. So computer science classifications kind of coarse. They tend to ignore the only distinction they make is between exponential and polynomial. But if I could find an algorithm that's scaled like n squared instead of n to the fourth in the database size, then that polynomial advantage can turn out to be an enormous factor in a large system. And we don't know how to prove bounds with that kind of accuracy. So that's an open problem. And also, there's a lot of problems which are known, classes of problems which are known to have hard instances, but many of the members of this class are actually easy to solve. And there are heuristic methods that will do a pretty good job on all of them, including the hard ones. And we don't know so much about quantum heuristics. That's another area where now that we have hardware, I think people are going to start hacking around and discovering these. And I think that'll make for great progress. Okay, so let me start at a really low level here. Information is physical. It's stored in and carried by physical systems. So you have to talk about physical bits or instantiations of bits, and then the bit of abstract information they might contain. They're different things. And for example, you can store 1 bit of information in the position of a single pole double throw switch. This switch open could be 0, switch closed could be 1. You can transmit that information that the bit is 1 by lighting a light bulb and sending it off particles of light to other persons. There are really only 2 possible encodings for classical bits. You can have 0 could be represented by switch uh, open, or 1 could be represented by switch open. Those are the 2 choices, and the 2 encodings just differ by a not operation. So it's not too complicated. And so that also means there's only one kind of error, bit flip, ignoring erasure errors, which I won't go into right now. So let's now compare all of this to quantum bits or qubits. Again, information is physical, but now the quantum information is stored not in a macroscopic switch or state of a transistor, but maybe in a single atom or an ion or this quantum state of a single particle of light, a photon, or what we work on, the quantized energy levels of superconducting circuits, or perhaps the quantized energy levels of mechanical oscillators. And all atoms and similar objects have quantized energy levels. And if you have access to the 2 lowest, if you can shine microwaves or a laser on an atom and cause transitions between these 2 states, then you've got yourself a quantum bit that you can flip and so forth. So I'm going to talk now about the fact that quantum information is both digital and analog. So why does it look digital? Well, the energy levels of a quantum system are discrete. And if I measure the energy of an atom when it's in one of these 2 states, I'll either get the energy corresponding to 0 or 1, never anything in between. So measurement of the state of the quantum bit always yields 1 classical bit of information, 0 or 1. And then there are all kinds of notations. I'll talk about excited state and ground state. If I'm a physicist, if I'm a computer scientist, I'll talk about 1 and 0. I'll use this Dirac notation, excited and ground, or if I do nuclear magnetic resonance, I'll talk about spin down and spin up. And if I talk about measuring the Z component of that spin, I'll make it dimensionless and take its values to be -1 and +1, which are more symmetric than 0 and 1, much beloved by computer scientists, but these are often preferred by physicists. So that was quantum information as digital, but it's also analog, because a quantum system that has 2 states like this can actually exist in an infinite number of intermediate states, superposition states, that are very familiar to those of you who've taken quantum mechanics. And they're kind of a mixture of 0 and 1. But that we don't use the word mixture. That has a specific technical meaning, but there are 2 complex numbers called probability amplitudes in front of these. And in the end, you can take 1 to be real. So in the end, there are really only 2 real parameters, this angle theta and this angle phi. So you can define, you can associate with every quantum state a unit vector, a so-called spin polarization vector. It may or may not have anything to do with the spin of an electron, say. And theta is the colatitude, and phi is the azimuthal angle here. And there's a continuum of such states, so it's analog. And the errors are analog. This arrow could accidentally drift around in position continuously like that. And yet remember that if I measure the energy, I always find the state either here or there. So it's has both digital and analog features. So another way to say this is that here's Alice, and she chooses a preferred axis, physicists call a quantization axis, to define her two basis states, z equals +1 and z equals -1, like ground and excited state of the atom. But Bob has freedom to choose out of a continuum of directions to align his measurement apparatus. So let's say he tilts his measurement uh, apparatus through an angle theta. Then in Bob's frame of reference, he sees Alice. Alice could prepare this state and hand it to Bob. In Bob's frame, it's a superposition of up and down. That is to say, z prime is +1 and z prime is -1. So let's see, I guess I'm doing it the other way around here. If Bob prepares z prime as +1 and hands it to Alice, Alice is going to see a superposition of her up and down basis states, and she'll measure z as +1 with probability cosine squared theta over 2, where that's the tilt angle, and z is -1 with probability sine squared theta over 2. So some randomness has suddenly entered the problem. Everything is continuous and smooth and nice here, and yet if Bob and Alice's axes are not aligned, randomness appears. Why is that? Well, and furthermore, I should say one more thing about that. If Alice measures that this is spin up, then she says, oh, Bob gave me a spin up. Actually, Bob gave her this, but her act of measurement produced this most of the time. Occasionally she'll find this, but she'll never know that Bob had prepared a superposition state because he used a different encoding than Alice was using. So there's this so-called state collapse or back action. And Alice has no way of knowing it happened, because if she measures this again, she will get the same result as the first time. So this leads to this wonderful expression that Sasha Korotkov likes to use, that in quantum mechanics, things are random, but you don't see what you get what you see. The act of looking brings into existence the state you are looking at. And you might ask, well, why are quantum measurement results random? And that's because we have to reconcile the fact that if Alice makes a measurement, she always gets one bit. She always gets a discrete set of one of two possibilities. And yet the encodings can be changed continuously. And there's no way to reconcile that smoothness with that discreteness unless you have randomness. So the measurement results are discrete, but the probability distribution for the measurement results is what varies continuously. So if this angle is 0, they're always going to agree on the result that cosine squared theta will be 1 and sine squared theta will be 0. Alice will always get the same result as Bob. If Bob turns his axis through pi, then the results will be also deterministic, but just opposite to what Alice will measure the opposite of what Bob did. But partway through, like at theta equals pi over 2, then Alice will just get a 50-50 even coin flip on each of her measurement results. So the only way to reconcile this discreteness of this discrete nature, binary nature of the measurement results with the continuous nature of the encodings is through continuously changing probability distributions, because there is randomness. So a classical register of n bits can be in one of 2 to the n states, but a quantum register can hold an exponentially large superposition of all possible 2 to the n states. Here, I've taken the complex numbers in front of each possible state of 3 qubits to be just plus or minus. It could be complex. They could have different magnitudes and phases, but you can see here that I have to choose plus and minus 2 to the n times. So already there's 2 to the 2 to the n choices. So it takes a lot of numbers to specify a state. And you can create these states very efficiently in a single time step on a quantum computer. So if you have even a small quantum computer, which today IBM and Google have machines with 50 or 60 qubits, um, the state space, the number of states that you can be in, just the number of basis states, is 2 to the 53. That's about 9. It's about 1 petabyte of numbers. And so it's very difficult to solve the equations of quantum mechanics for the operation of this computer if you're trying to do it on a classical supercomputer. So you don't need millions of qubits in a quantum computer to have it be very powerful, provided that there aren't any noise and errors, and which is the part we don't have yet. So in this giant superposition, our answer is in there somewhere. It's got all possible states there. But the problem is that when you measure, you get a random state collapse to one of these possibilities, not necessarily the one that's the answer. So that's bad. So how can we get quantum algorithms to produce useful results instead of random noise due to this state collapse feature? Well, the way a quantum computer works or an algorithm works is that these complex amplitudes in front of these states are kind of like wave amplitudes, and we have to arrange destructive interference among all the wrong ones to kill off their amplitudes, and constructive interference among all the correct answers, so that when you make a measurement in the output register, you have a high probability of getting the correct answer. And so you can kind of think of a quantum computer and its algorithm as a kind of programmable diffraction grating. You have these wave-like superpositions at the input. They're propagating through the quantum computer, and you adjust their path lengths and phases, and you block certain paths in such a way that you get many waves arriving at the right answer in the output register and very few at the wrong answer. So that's just a crude metaphor, but that's roughly how quantum computers work. But it also is why, but there aren't actually that many known quantum algorithms, because uh, computer scientists and physicists don't have such great intuition for how to make these interference effects work in our favor by writing code. All right, well, now that you're experts, here's a quiz. Don't panic, I'll give you the answers. Is quantum information carried by waves or particles? Yes. Is quantum information analog or digital? Well, I've just showed you the answer is, again, yes. Okay, so what kind of hardware do we use to build quantum computers? Well, you can have what are called ion traps. Individual ionized atoms can be trapped in small groups of 30 or so, and you can manipulate their quantum states. There are things called Rydberg atom arrays, cold atoms. that have one electron excited to a very high excitation level. There are quantum dots in silicon, where a sort of artificial atom with a few electrons trapped in a piece of silicon. And then the thing we're working on here at Yale is superconducting electrical circuits. And then, there could be some new technology out there that we haven't thought of yet that could be much better. So the first all-electronic quantum processor was built here at Yale in 2009 in Beckton Labs. It was a huge computer that had 2 quantum bits in it, and they were able to talk to each other by exchanging microwave photons. If one was in the excited state, it could send its excitation through this resonator to the other one. And such circuits are pretty much analogous to, baby integrated circuits in regular computer chips. They're produced by optical and electron beam lithography, just like in a Intel facility, much cruder here, of course. But we replace the semiconductors by superconductors, metals that lose all electrical resistance when you cool them down near absolute zero. And so all of the machines you've been hearing about, the Google quantum supremacy machine, the IBM Q machine, Intel, Rigetti, these are all direct, very massive engineering scale-ups of this first device built here at Yale just over a decade ago. So here's Daniel Sank with the CEO of Alpha. Daniel took Physics 261 with me. Here's Chad Rigetti. He was a PhD student of Michel Devoret. I was on his thesis committee. He's founded a very big startup. Here's Hani Pike, who is a postdoc with Rob Sholkoff. She's one of the members of the IBM team. There's a startup based on the Yale technology here in New Haven, and Intel and Microsoft and Northrop Grumman, lots of companies and startups are getting involved in this business. So how do we make an artificial atom out of electrical circuits to be our quantum bit, to hold our quantum information? So this is a so-called transmon qubit. It's evaporated film of superconducting aluminum, 2 pieces about 1 millimeter long, forming 2 halves of a dipole antenna. It's evaporated on a special sapphire substrate, which is an extremely good insulator. And then the 2 halves of the antenna pads are connected together by a Josephson tunnel junction. It's 2 little pieces of aluminum that overlap with a little bit of oxide insulating barrier between them. Very small, 200 nanometers on the side here, made in the Beckton and Malone clean rooms. And the excitations of this atom, remember, this is superconducting. The electrons travel together in pairs without any electrical resistance, and they kind of form one giant quantum state, and they slosh back and forth through the tunnel junction. And the excitations of this sort of oscillator are the excited states of our artificial atom. And the energy quanta of this excitation, which is at about, in the microwave frequency, near cell phone frequency, sort of 5 gigahertz, instead of like in hydrogen atom, where this is an ultraviolet optical transition. So the superconductivity turns out to make the spectrum of this atom extremely simple. It's an anharmonic oscillator. The energy levels are not quite evenly spaced, but unlike hydrogen, there's no fine structure or hyperfine structure. The quality factor, the frequency times the lifetime of the excited state before it falls down, is comparable to that of hydrogen. And but where it beats hydrogen is it's got its own antenna built in. The oscillations in the excitations correspond to several pairs of electrons moving a millimeter. So that produces huge, relatively speaking, currents and voltages that couple extremely strongly to microwave photons, which is how we talk to, measure, and control these artificial atoms. And this idea of having artificial superconducting atoms talking to microwave photons in electrical circuits we call circuit quantum electrodynamics, or circuit QED. Why do we have to cool these things down to near absolute zero? Well, first, the aluminum becomes superconducting only below about 1 Kelvin, just above absolute zero. And also, the small size of Planck's constant, which connects frequency and energy, means that microwave photons at 21 gigahertz have an energy that's comparable to the thermal energy that's around when you're at 1 Kelvin. And this is at 5 gigahertz, so it's only like corresponds to a quarter of a Kelvin. So a temperature of 5 Kelvin looks red hot to these poor atoms. You have to cool them down to 1/100th of a degree above absolute zero in order to have them land in their ground state. Okay. Still getting used to having multiple screens here, sorry. So the huge information content of quantum superpositions that gives the power to our quantum computer also comes with a price. It's the Achilles heel. These superpositions are extremely sensitive to noise, perturbations, and dissipation. And for example, this superposition with a certain wave amplitude plus and can become minus after a finite time called the coherence time, or T2. And that can be shockingly short. It can be, a microsecond. But despite this extreme sensitivity, we've made a lot of progress in increasing qubit coherence times. When the first superconducting qubit was invented by Nakamura in 1999, its coherence was immeasurably short. And since then, we've managed to increase the times by 5 or so orders of magnitude. They got high enough about 5 years ago that people stopped trying harder because now they worked well enough that you could do simple algorithms and so forth. But now the purpose of this center that I direct is try to get this push to continue upward. But no matter how much progress we make in improving the coherence times, you have to contend with what I modestly call Girvin's law of physics, which is that there's no such thing as too much coherence. We need quantum error correction. And that's much more subtle and interesting than in classical computer. So here's the quantum error correction problem in a nutshell. And this is a topic on which many of us at Yale are working very hard right now. I'm going to give you an unknown quantum state, a superposition of 0 and 1. And I'm not going to tell you what the superposition coefficients are. And if you measure it to look for an error, you're going to randomly change it and collapse the state due to this back action. And your task is, if it develops an error, please fix it. So how in the world can you do that? But miraculously, it actually can be done. And this same Peter Shor, who invented the factoring algorithm, helped invent quantum error correction. And the basic idea, just as in classical error correction, is to store the information redundantly in what's called a logical qubit. The information is stored non-locally in entanglements among these qubits. It's spread out over multiple physical systems, so it's hard to find. It's sort of hidden from the noise. And non-locally means that there's no single one of these physical qubits that, quote, knows the state of the logical qubit, whether we're storing a logical 0 or 1 or a particular superposition. Because if it did know that, then, the environment could measure, or the one of the qubits could collapse due to spontaneous emission of a photon or something. And then the environment would know the logical state and everything would collapse and it would be ruined. So you have to be able to make special multi-qubit correlation measurements in order to figure out what error has occurred without learning anything about what logical state the error occurred in. And this seems very hard because remember, the errors are analog, they're continuous. And it's a well understood in classical electrical engineering that you really can't error correct analog devices. But measured errors, remember, are discrete. All measurements yield discrete results. And so you can figure out, it turns out, that saves you. You can figure out what errors occurred. In fact, the active measurement discretizes what error occurred. It's no longer continuous. And that helps you do error correction. So the idea is to build a kind of Maxwell demon, which is constantly measuring and removing errors. It's like trying to pump entropy out of our quantum computer into a cold bath. But the big problem is that if you need n qubits, like here you need 9 qubits to represent one logical bit, all 9 of those are having their own errors. So it happens 9 times faster. So you've taken a giant step backward. You've made the error rate 9 times worse. And the Maxwell demon has to be so fast and so accurate to overcome this factor of 9 and even go beyond that, so that the lifetime of this logical information is longer than if it had just been stored in a single unencoded physical qubit. And of course, this is made of similar parts as this, and so it has its own errors. And amazingly, there's this concept of fault tolerance, which is roughly, it is possible to design error correction circuits that will still work and correct errors, even though the circuit itself makes errors. And this is called the, who will watch the watchman problem. You assign a watchman to look for problems, but who's going to check the watchman isn't having problems. So so this is the real grand challenge for the field. And we're just at the beginnings of making progress on this. And so I think I'm running out of time. So I'm going to just wrap up here by saying that we have done some of the first experiments that actually got quantum error correction to make the lifetime of the quantum state longer instead of shorter. And the idea is to not store the information in material objects. Don't use material objects as qubits, but use microwave photon states stored in high Q superconducting oscillators or resonators. And that part of the discussion is more complicated, so maybe I will skip over that and just jump down here to my conclusions. We're still in very early days of learning how to do more and more complicated engineering tasks that are needed to get to our goal of truly fault tolerant, useful quantum computation. And there's just lots of work that still needs to be done. And young people like you are going to help us get there. I hope it's going to take a while. And so I hope I've convinced you that quantum mechanics is strange and wondrous, and you have to think different. And the second quantum revolution is based on a new understanding of the old quantum mechanics, that weirdness is a feature, not a bug. So I'll stop there. Thank you, and happy to take questions.
Oh, Professor Girvin, thanks so much for that talk. Yeah, so big round of applause.
Thank you.
I got some questions, so I'll start with those, and then we can open it up to just people raising their hand, and I'll call on you, and you can ask your question. So yeah, so Ben sent a question. So he said, if we aren't building the analogous quantum transistors, or maybe at the transistor scale yet, how can Google claim to have achieved quantum supremacy?
So quantum supremacy is, I mean, they built an amazing machine. It's a huge scale up of that first crude device I showed you built here at Yale. The Google machine has 50, well, they built 54 qubits. One was broken, so they have 53. Very complex control system. Amazingly complex device. And they chose a special problem, a sampling problem, using the randomness of the measurement results. The challenge was to build a machine, classical or quantum, that can produce samples from a very complicated probability distribution. So bit strings, random bit strings that are not independent of each other. They're correlated in very subtle ways. It's a completely useless, almost completely useless problem, but it was special design because it was easy for them and hard for existing quantum computers. So that's how they, and they did, it's highly non-trivial achievement. And they still got to check all the details, and there's still arguments going on. But I think pretty much they did demonstrate barely some quantum supremacy, but it's on a useless problem. So the name of our center has quantum advantage in it. What we mean by quantum advantage is, a quantum computer that it does something useful, has advantage over classical computers.
So I guess on a related note, a related question, what are some of these nearest or NISQ term quantum areas for quantum advantage?
Well, yeah, so that's an open research topic. People are thinking about choosing problems, using the same trick, choosing a problem that's especially easy for the type of hardware we have, but we want it to be a problem that's actually of interest to, it's not just producing some random numbers with funny correlations. It's solving an interesting optimization problem, or factoring numbers or whatever. So that's still on top. It's not, we don't fully know the answer to that. There are different ideas for tasks that we know are important, and we're not necessarily sure there is quantum advantage, or if theoretically there is, we're not sure whether it's the right problem to choose for our not very good hardware yet, and so forth. So that's one of the things we're looking at. We're working at materials, devices, software, and algorithms, the full stack, and trying to co-design, doing things together, trying to make each layer of the stack 10 times better, but in a way which doesn't ruin the chance for the other layers to get their factor of 10. Like, you can make a qubit that's 10 times better, but nobody can use it or something. I mean, that's, so we're trying to work together all the way from picking an algorithm, for example, quantum field theory, of a type lattice QCD, something like that, or maybe baby versions of that, that's of interest in particle physics and nuclear physics. We're trying to understand right now, how hard would that be to simulate if we had somewhat better, but not infinitely better quantum computers than we have right now. And we don't know the answer yet. So it's still the answer to your question is a research problem.
Yeah, absolutely. Hopefully, you know, some of the people here can tackle that research problem.
Right.
So does anyone from the audience have any questions? Feel free to just unmute and start talking.
Don't be shy.
Okay, I mean, I guess just jumping off of that last thing, since the people in this call are going to be the ones solving these like great problems, what are some advice you would give to young people like ourselves, wanting to get into the field of quantum?
Well, it's an interesting field because I think to solve the problems we have, it's going to have to be very interdisciplinary. We need electrical engineers who understand extremely high-speed control systems. We need computer scientists to learn a little bit of quantum. They can't take 7 years and get a PhD in physics and one in computer science. So we have to learn how to communicate with each other in from different backgrounds. So some practice working in interdisciplinary teams like that is useful. You should certainly learn some quantum mechanics by taking at least some course. But if you're a physicist, you should take a computer science course. If you're an electrical engineer, depending on your specialty, you might be a computer architect. You're going to need to take some theory courses. You're going to have to be have enough breadth. You can't understand everything deeply, but enough breadth that you can communicate with people who understand the things you don't deeply. And, you know, pick stuff that's fun. That's the main rule in life.
And I should note that Professor Girvin is the faculty advisor of like the UQC club, the Yale Undergrad Quantum Computing Club. And one of the things that I think makes the club really awesome is that our membership come from different backgrounds, right? Like we have people from computer science and from chemistry, from economics, from physics.
Right.
So that they can come up with really cool projects like a cryptography project, right? Or some sort of API or some sort of chemistry.
Yep.
Yeah.
Yep.
Yeah. So does anyone else have any questions? Feel free to speak up.
I'd like to ask a question about the extent to which quantum computers could potentially replace classical computers in the future. So my understanding is that this kind of bug that the quantum computer only actually lasts for a very short time can't really be avoided. So should we expect, having quantum smartwatches in the future and like quantum smartphones, or will quantum computers always remain a kind of very specialized piece of hardware?
I think they'll, for the foreseeable future, they'll remain very large, expensive pieces of hardware, which in some technologies have to be inside a refrigerator. So they'll be accessed over either the classical or the quantum internet. So we anticipate, through our center and the other centers, that the lifetimes of the physical qubits will be improved substantially over the next 5 years by advances in materials. And using quantum error correction, we think we can advance that then to the logical qubit lifetimes that are quite long. I mean, if we can't do that, then we have a serious problem. But I don't think the statement that it can't be extended is really well. We're basing all our work on the assumption that we're going to solve that problem. But it's right now, 100 microseconds is considered a really long lifetime. The clock speeds are pretty high, gigahertz clock speeds. So you can do hundreds or thousands of operations in that short length of time. But we're going to need much longer coherence times, a second or a minute eventually, by having lots of layers of error correction if we're going to solve big, difficult problems. And although the hardware overhead of having all those redundant qubits and extra measurements and so forth and so on, that makes it too big to fit in your cell phone. That's why they're going to be central. We're going to recapitulate the mainframe era of the 1960s for the foreseeable future.
Awesome. Does anyone else have a question?
I was just curious. I'm sorry, my video is off. But Professor Girvin, you just mentioned the phrase of like a classical internet or quantum internet.
Yeah.
What do you think a quantum internet could look like?
Well, that's one of the other things that we and some of the other centers are working on. So what I mean by that is you can send information with some sort of flying qubit, like a photon that can be polarized vertically or horizontally or partway in between, for example. And it can be in a superposition of different polarization states such that if you look at it and measure it, it collapses. So you can actually send quantum bits, let's say, over an optical fiber to a remote computer. And you can do interesting things with that. You can sort of encrypt the program that you're sending to the computer to do oblivious computing. So if you don't trust the owner of the computer, then maybe they're going to spy on what you're working on. They can't. There's a way for you to prevent that from happening if you have quantum access. You can send quantum data directly to the computer as opposed to classical data. Classical data, someone can look at and copy, but quantum data, because when you look at it, it changes. There's a no cloning theorem says it can't be copied. So that gives you this quantum internet gives you extra power. You can remotely entangle two computers in different states, different counties or countries, and that can lead to extra computational power. You can synchronize atomic clocks much better if you have a quantum internet, for example.
Very cool. Does anyone have another question? We'll take two more questions.
So Professor Girvin, I'd like to ask another question. So you kind of touched upon this here. What are some of the main implications of quantum computing on cybersecurity? Often we hear things like, oh yeah, like the RSA encryption algorithm is foolproof, except if you have a quantum computer, which can crack it. So I was wondering about where that advantage can come from.
Yeah, so there's two sides, right? Offense and defense, so the first Shor algorithms, people realize, oh, it can break the RSA encryption algorithm, which relies on this one-way problem that it's hard to find prime factors, but it's easy to check that you have the right ones. But then people realized if you had a quantum internet and you could send your messages as quantum bits, then you can prevent an eavesdropper from decoding the messages. So it's provably secure because of the laws of quantum mechanics. And actually, we're having a talk in my center tomorrow by Peter Shor, who's going to talk about quantum money, which is a sort of version of quantum encryption. So in the end, it turns out in the battle between the people with the clever quantum algorithms and the people with the clever quantum communication protocols, that privacy wins out. That even if you have a powerful quantum computer, there are quantum encryption schemes that can't be broken even by a quantum computer.
Well, is there one more question? If not, then I actually had one question for you. So you've talked about a bit about different physical platforms to implement quantum computers, qubits. Do you think that certain platforms are better suited for certain applications like quantum communications or quantum memory or processing?
Yeah, no, that's a good question. I think ultimately, just there'll be all kinds of hybrid architectures and hybrid equipment in a quantum computer cluster. So naturally occurring atoms or rare earth atoms stuck inside a solid matrix have very nice optical properties. So if you could, one of the things we're working on is converting quantum information from microwave frequencies to telecom frequencies so that you can send it through optical fiber. There are things we can do at microwave frequencies like error correction that nobody knows how to do at optical frequencies, but we don't know how to send the microwave photons long distances. So we need hybrid devices that are superconducting and involve real atoms and real optical photons and stuff. And there may be, maybe there's a particular kind of qubit that has a really long lifetime, but it's hard to manipulate. Well, that might be good for long-term memory storage. So I think, we're so desperate for performance that we're looking at all kinds of possibilities for things that don't have a long lifetime but can be manipulated very quickly. So you can do lots of operations anyway. Kind of by definition, if you can do operations quickly, then your thing is too much coupled to the outside world to have a long lifetime. This is the engineering challenge. So there'll be all kinds of different materials and qubit types and data structures and physical structures that will go into a large scale quantum computer.
Wow, that's very exciting, especially from like a research standpoint. So
yeah, I mean, there might be trapped ions and, all kinds of things could happen, right?
Well, that's the end of our time. Thanks so much to Professor Girvin for giving this amazing introduction and kicking off this speaker series that's been arranged by our director of invited talks, Eugene. Yeah, thanks so much. Thanks so much for coming, Professor.
My pleasure, and I'm glad you guys are organizing this, and I hope you're having fun.
Yeah, so big round of applause. Yeah. And stay tuned for our future talks. They'll all be undergrad accessible, and they'll give a good survey of what's out there in the quantum world.
Okay, bye-bye.
Bye-bye.